This is part 2 of the normal distribution where we calculate out the p-value by hand. We do so by using this formula to figure out what the z-score is. The z-score is just a standardized number where we have all sorts of information about. X is the value in question that we're determining to relate to the standard deviation, the mean, and the standard deviation here. Take Joe, for instance. He takes the ACT, and the people who are in charge of the ACT tell us that the mean score is 22 and that the standard deviation is 4. If Joe scores 25 on the ACT, and we want to know, he did better than what percent of people? Well, if we use this formula here, we can determine the z by putting 25 in for x and 22 in for the mean and 4 for the standard deviation. When we calculate this out, we find that the z-score is 0.75. Okay, now there is a set of charts that can be found anywhere that probability and statistics is talked about, and it looks similar to this. There's two parts to this chart. This part of the chart is the z-scores, here and here, and the beefy part of the chart represents proportion, or can be referred to as proportion of observations, or probability, percent, also known as the p-value. All of these start with p, so p-value is very fitting. If we look at the charts, on top there is a standard deviation curve. Up to here, the left side on both of these charts are shaded. These ones represent positive z-scores, and these are negative z-scores. So our z-score is 0.75. So to find that on the chart, we start at the left. It's positive, so we go to the right side of these two charts and find 0.7, which is here. Along the top is numbers that say 0.0 something. These represent the second digit in the hundredths place here. So, if we go to follow here and cross it with the 5, we get our p-value. So, it was 0.7734. In other words, Joe scored better than 77.34% of people. Now, it's useful to determine everything to a z-score because we can compare things that don't have similar scales. Let's say we want to see who did better, Joe on the ACT or Sue on the SAT. Now, she took the SAT and was determined that the mean was 500 and the standard deviation was 100. Sue scored a 650. So if we determine what the z is from the formula, 650 goes in for x, the mean is 500, and the standard deviation is 100. So, after calculating that out, her z-score is 1.50. So, using the same method, we come here and we find 1.5 on the z-chart and 0 for the second digit. So, when we match these up, this is the p-value that we get. So, she had a p-value of 0.9332. In other words, she scored better than 93.32% of people. So we can compare Sue and Joe, even though they are not the same scales, and determine that Sue did way better than Joe did. Now, if we wanted to work backwards in essence, where we want to say If Joe wants to score in the top 10% of all people who take the ACT, okay? So if we drew out a chart here, he would be top 10%, somewhere in here. And we want to determine what score does he at least have to get in order to fall into this category here. Well, in order to use this chart and information, we have to make sure that the shaded part on this graph matches the shaded areas here, which it does not. So before we can do anything, we have to take 100% and subtract that 10%, which gives us 90% here. So we have to look in our chart because it gives us the percent. And we have to find the closest thing there is to 90%, or 0.9. So if we're looking in our chart, we find that 0.997, or 0.8997 and 0.9015 are the two closest numbers. So, which one of these ones is closer to 0.9? Well, this one. So, we know if we follow this along the chart here, that the z-score is 1.38. Now, based off of our original equation down here where z equals the x minus mean over standard deviation, if we arrange that algebraically, solving for x, this is the formula that we get here. So if we put in our values, that's for x, and the standard deviation was 100, and the mean was 500. When we calculate that out, x comes out to be 27.52. So, in order to be in the top 10%, he has to score at least 28 on his test. Now, let's say we're looking at Sue, and she wants to know what score she needs to get to be in the 80 percentile. 80 percentile means better than 80% of people. Since it matches this side of the chart, we can go ahead and calculate it by hand, or we can put it in the calculator. Now, since we're working backwards, we don't use this first one where we find the p-value. We have the p-value. So we're going to use these steps here. Second bars to get the distribution menu. And you're going to arrow down to the third option here, inverse normal. After you push enter, you're going to put in whatever p-value was. So in this case, we're looking for 80%. And the mean for this SAT is 500, and the standard deviation is 100. So when we calculate that out, it gives us that x equals 27.52. And so she must get at least, that comes out to be 584.16. So she has to get at least a 585 to be at the, 585 to be at the 80 percentile. And I'm sorry, over here, I wrote this wrong. The standard deviation here was 4, and the mean was 22. My mistake. But it does come out to be 28 here. Okay, so you can use the calculator, or you can use these charts when determining what p-values are and the z-scores. And that's all there is to it, to calculating the p-value from mean and standard deviation.